Hello and welcome to the Chemistry Tutor. My name is Jason. I'm going to be your teacher here during this course. And what you're going to find is that during the entire DVD series where we talk about chemistry, we're going to take every single topic from step-by-step chunks, manageable chunks, and we're going to build your knowledge in small little incremental measurable steps so that every step along the way you're going to be able to follow everything that's going on. Before you know it, you'll be balancing chemical reactions and calculating the yield of a chemical reaction without any problems. Now, I will tell you that chemistry is one of the subjects that a lot of students really do have trouble with when we first begin. When we start taking chemistry, when we grow up a little bit, we take that kind of class. The reason is that almost every single problem that you are going to have in your chemistry class is going to be a word problem. So a lot of people don't like word problems. You have to read it, and more than that, you have to understand it. That's really the challenge there. The number one thing that students do wrong when they read a word problem, read a chemistry problem, is that they'll try to take the numbers in the problem and add them or subtract them or do something to them to try to get to the answer without really reading and seeing what the problem's really and truly asking you to do. And that really is the key. You have to read it, you have to understand what is being asked and what you were given so that you can outline a logical path from start to finish. And that's the kind of skill base that we're going to get when we do these problems in this class, because all of the problems that we do here are going to also be word problems to give you that practice there. Now let me jump back a little bit. Chemistry is incredibly interesting. It's one of the few branches of science that you can really study in whole and really feel like you have an everyday connection to it. And that's why I think it's so interesting. I love and enjoy physics. I have a degree in physics. It's really neat. But when you start getting into advanced physics, you really lose the ability to visualize what's happening. When you have a electric field or something in a room, it's invisible. You can't touch it. You can't taste it. You can't see it. So it's very interesting. I love that stuff, but it's not very tangible a lot of times when you get into the advanced stuff. But chemistry is something that you can open up your kitchen, open up your refrigerator, and see things that were made chemically all around you. So it's something that you come into everyday contact with, The plastic that you use when you put it in a Ziploc bag or a zippy bag or something and throw it in the freezer, some kind of food. That plastic is a long chain of atoms that are bonded together, and someone designed that chemical to be strong, to be plastic and pliable so we can move it, to be temperature resistant. It was engineered to serve a function, and they built it, they put it together, and we use it every day. Aluminum foil, that thin sheet aluminum foil, very, very useful. It's, people go in the factories, figure out how to extrude that aluminum, figure out how to make it flat so that we can use it. All the way to rocket science, the most powerful, I shouldn't say the most powerful, but one of the most powerful and energetic chemical reactions that there is if you take hydrogen gas, or liquid hydrogen, if it's liquefied, that's the same stuff. The hydrogen is the same stuff that we put in the Hindenburg years ago. Unfortunately burned and went up in flames, but hydrogen, and you take oxygen, right, and you put them together and mix them together, two very simple things off the periodic table. You mix them and you ignite them, and what do you produce? Water, right? But it's a very energetic reaction. We also produce a lot of heat, and that causes those gases to go really, really fast right out the back of a rocket engine, and that's one of the most powerful rocket fuels that we have. So we go all the way to rocket science. We can really understand how chemistry can boost a rocket into space, all the way back down to your kitchen. If you take, some baking soda right off of the shelf, and you take some ordinary vinegar right off the shelf, and you put some baking soda in the cup, you pour some vinegar right on top of it. You don't have to light it. You don't have to blow on it. You don't have to cool it. You don't have to heat it. But just the act of pouring those two things together will cause a chemical reaction to happen, to bubble up, producing a gas, and we'll talk all about that stuff a little bit later. But I guess the point I'm trying to make is that chemistry really is all around you. When you have a matchbook, and you strike the tip of that match, that's a chemical that someone has designed and tested and put on the tip of that match to serve a function. Plastic, cars, rubber, it's everywhere. And a lot of students have difficulty with this class, but we're going to break down those barriers here. Now there's one final note that I'm going to tell you here as a sort of a piece of advice before we get started on this journey. And that is that even though a lot of students have problems with chemistry, there are two main reasons that we have these problems. The first reason is because the definitions, right? The definitions. That is the most important thing. We really have to make sure we know what we're talking about. So when I tell you that I'm talking about a molecule, you really think you understand what I'm talking about. Everyone has their ideas. You may have your own idea what a molecule is right now. Maybe you're correct, maybe you're not, but we have to make sure we're on the same page. Definitions are key. So that's really what this section is going to be, a lot of definitions. I'll try to make it a little interesting, but basically you have to have the terminology down. The second thing is what I talked about before. Very, very important when we read our problems, not just to kind of glance through picking out numbers. That's not what we're doing. We need to really read it and really understand it. With that, you'll know what to do. The other thing I'll say is that when you're doing chemistry problems, to be truthful, most of the time, you're just going to be adding, subtracting, multiplying, and dividing, right? I don't want to say there aren't any equations or formulas in chemistry, because there are, but when you compare chemistry to maybe physics or something, physics is chock full of equations. You have to understand the equations. Chemistry, you really don't have too many equations, but you have a ton of concepts, and we have to understand those concepts. But you're not going to get any higher in the math more than addition, subtraction, multiplication, and division most of the time. So pat yourself on the back. If you know how to add, you know how to multiply, divide, and subtract, you're in pretty good shape. But what we need to do together is build the logic. So we're going to do that here. All right, so what is chemistry? That's the number one thing we need to answer. I think most people have a pretty good idea about what chemistry is, but let's explore it together. If I had to write a definition for chemistry, and I had to keep it short and sweet, my definition is the following. It's the study of the composition and structure of matter and changes that occur in matter. Now, one thing I'll say for everyone here listening is that when I write definitions, and I try not to front load all of the lectures with definitions, but we just have to do it in this case, I'm going to generally write them down because it helps me articulate what we're saying. It forces me to read every word, and I think it forces you to read every word. So I could blast the screen here with a large definition that you have to kind of scan through, but I think there's something gained in reading every word as it goes up on the board, just like a regular classroom. So that's what we're going to do. Chemistry is, this definition pretty much should fall in line with what you probably have in your head. It's the study of the composition and structure of matter and changes that occur in matter. When we say changes that occur in matter, we're talking mostly about chemical reactions. That's mostly what we're talking about. So we're going to spend a good chunk of time in the beginning of the class talking about what is an element. How do you calculate? How do you figure out how elements join together? And then once we understand that, we're going to combine different things in a chemical reaction to form a new product. Hydrogen plus oxygen gives you water. Carbon plus oxygen gives you carbon dioxide or carbon monoxide. How does all that come together? How do we know what's going to be formed and how much of it will be formed if we put, different amounts of chemicals together? How much of the stuff is going to come out the other end? That's really what we're trying to do in chemistry. It's one of the most important things. So I've given you a couple of examples, but if I had to give you a couple of additional examples, what about wood when we burn it? When wood burns, right? If we take a piece of wood and we put a match to it, what happens? Well, we get a lot of smoke and we get some heat, right? That is a chemical reaction. Oxygen in the air is combining with, basically it's combining with the wood and everything else in the wood. We get carbon dioxide, and then of course the particles that we see, the smoke is just the little particles that have, after they've been burned, floating up into the sky. But we have carbon dioxide and a host of other things that come out of burning. That's a chemical reaction. What else do we have? Something maybe you may or may not have thought of as a chemical reaction. What if we take iron and we watch it rust? Well, what happens here is we have the iron reacts with the oxygen And what we get out of that is iron oxide. Now notice I'm not writing this down into a chemical reaction in terms of the elements combining and giving you a chemical formula on the end. We're going to get into all that stuff later. Right now we're just trying to build the concepts. This is an example of the stuff that we're going to really study in chemistry. You take something like iron, you just let it sit in the atmosphere. Over time, the oxygen will combine with that iron spontaneously. It's just a natural process. And out the other end, you'll get what we call iron oxide, which is rust, which is orangish, material. Almost the entire surface of Mars is iron oxide, so it's been oxidizing for a long time. But if you take a piece of iron, stick it outside, 5 months later, come back, you'll see some kind of brownish, reddish coloring on it. That's a chemical reaction. All right, and we already talked about rocket fuel. When we take hydrogen and oxygen, we combine them together, we get water. Of course, we also get heat out of it because that's a reaction that has heat involved in it also. All right, so that's just a general idea, general overview of chemistry in general, the kind of things that we're going to be looking at. Now, obviously, chemistry is a mathematical science, so we're not just going to be writing words down. We'll have elements and we'll have amounts and in terms of how much of things that we mix together and how much is produced, and that's what we're going to be interested in calculating. Now, in order to get anywhere else in our journey in chemistry, we have to follow sort of a logical sequence. Some of the stuff I'm about to tell you, you probably already know from second grade. I'm pretty sure most of you already know that everything is made of atoms. But what we need to do is start at the beginning. Maybe there's a nugget in there that you didn't quite know, but no matter what, we need to start at the beginning and make sure that you understand everything so that as we get to the end, I'll build you up so that nothing will be left out. So, if you understand what an atom is, you'll understand our first little guy right here. What we have is the concept of an atom. And for those of you who know what this is and maybe haven't revisited it in a long time, we'll just talk about it here. It's basically the smallest elemental. And by the way, there are a million definitions for an atom you could write down, but this is mine. Smallest elemental unit in a sample of matter. All right, so what are some examples of atoms? They're things that you've heard of, that you've played with, that you've touched, and even that you've breathed. What about the atom of oxygen? All right, the chemical symbol for oxygen is the letter O, right? So that is an atom. We also call it an element because I'm kind of alluding to a few things here that we'll conquer here in a little bit, but there's a periodic table of all of the elements that we know about. And those elements are basically arranged. So everything in the universe that we know about is made up of these elements, which are just different kinds of atoms. And they combine in different ways, much like hydrogen is a gas, it's explosive. Oxygen is a gas, colorless, odorless, but we breathe it, we use it, right? You take those two things together, they chemically react and form water. Now, water doesn't look anything like hydrogen, and water doesn't look anything like oxygen. So when you combine these things together, they form new substances whose properties are totally different from the basic things that they're made of. So that's why we have so many different things around us that look totally different. The plastic in a bag, the rubber in a tire, the glass in your house, they're all made of atoms, which are just combinations of different, or I should say they're made of different combinations of these atoms, which are these elements that we have all around us. So an example of an atom is the element oxygen, chemical symbol O. How about nitrogen? Probably heard of this. Chemical symbol is N. Our atmosphere is made of mostly nitrogen, believe it or not, and about 20% oxygen. So we have this stuff floating around, you're breathing it right now. What about carbon? The chemical symbol for that is the element C. We represent C for carbon, N for nitrogen, O for oxygen, right? Carbon is, in charcoal. Carbon's in everything. It's in your body, it's in wood, anything living. Carbon, we're going to learn later, is an incredibly versatile element. It bonds in ways that other elements don't, and that's why life is really built on carbon, because it's really kind of unique and kind of cool. What about iron? We talked a little bit about iron. What would be the chemical symbol of that? You'd think the chemical symbol for iron would be I, but it's not. It's actually, if you look on your periodic table, it's Fe. And I'm kind of bringing this up because you'll see that a lot of times. Some of these elements, the chemical symbol will be the same letter as the first or the letter as the first letter in the name, but for some of them it's going to look totally different, and that's because you have to understand a lot of the scientists who were originally doing chemistry, they worked in Latin. The original language of science was Latin, especially when you're naming things. So Fe, just as a singular example, comes from the Latin ferrous, right? So that's where it comes from. Now, if you look in your periodic table, you're going to notice a good handful that don't match the first letter here. And that's because it's some Latin root. You could probably look it up somewhere if you were curious. But you're just going to have to get used to Fe being iron. Sodium is another example. Sodium. You might have heard of sodium. It's an essential thing that your body needs. Sodium is in table salt, sodium chloride. But sodium is not SO or S. Sodium is actually Na. In chlorine, just as an example. Cl. Now this one obeys, or sort of obeys. CHLCl is how we abbreviate for chlorine. So there's tons of elements, tons of different atoms in the periodic table. I just put a handful here just to kind of break down the barriers a little bit and help you realize that these mysterious things that we call elements, these mysterious things that we call atoms, they are things that are all around you. You've definitely touched carbon, you've definitely breathed oxygen, you've definitely, touched and handled all of these things in your life before, maybe in microscopic amounts, so you really didn't know about it. So, the concept of an atom, if you take anything apart far enough, if you take that water and you break it apart and you get that hydrogen and you get that oxygen, those are going to be the fundamental building blocks of what we call the elements. Now, I am going to go and give you a little bit of a segue here because I'm a physics guy at heart. That's sort of, my first love was always chemistry, but I ended up pursuing physics a little bit later in life. But I'm going to go ahead and tell you now that now we know with modern science that you can actually take an atom here and break that atom up into what we're going to talk about a little bit later, the protons, the neutrons, and the electrons that form that atom. And we'll get into that a little bit later, so don't worry about it. We're going to talk about those things. And furthermore, you can actually take a proton or a neutron and you can split them up even more into these even tinier subatomic particles. That's why they call them subatomic. Subatomic because they're smaller than the atomic particles in the nucleus there. And you can split them up even more. So really there's no end to how much you can split these things up. But when we say in the chemistry books that an atom is the smallest elemental unit of a sample of matter, what we mean is that if you break them up, that's the smallest unit where everything sort of retains some identity. In other words, if you get down to a chlorine atom, it's going to have some properties. Chlorine will kill you. Pure chlorine, if you breathe it, will kill you, just like that, right? Sodium is extremely reactive. If you take sodium and you put it in a bucket of water, it will spontaneously burst into flames. No match, no nothing. It'll just start igniting, right? So these are different properties because these are different atoms. But if you bust these atoms apart into the protons and the neutrons, then you sort of lose the identity of what the thing was, because all the protons really look the same. All the neutrons really look the same inside of an atom. All the electrons really look the same. So when we say an atom's the smallest elemental unit, we're not saying you can't break an atom apart anymore. We're just saying that that's the smallest unit where things sort of have some identity, different properties, right? Different melting points, different reactivity, things like that. All right, so that's an atom. Now what happens if you take some of these atoms and put it together? We already talked about that a little bit. If we take carbon and put it with oxygen, we might get carbon dioxide. We might get carbon monoxide. Both of those gases will kill you if you breathe them, too much anyway. And our body produces carbon dioxide, you already know that as well. So let's talk a little bit about the molecule. Now keep in mind, we are going to revisit these things, especially the molecules, and spend a good chunk of this course talking about how molecules are formed. This is just an introductory thing. What this is, a molecule is a larger unit in which two or more atoms are joined together. And that's kind of, I think, what most people think about when they think about a molecule. They think about this chemically joined thing that has some properties, like the water molecule. That's probably the most common molecule everybody knows about. We drink it every day. It's oxygen and hydrogen put together. And so I'm going to take this opportunity to write down something that I know you already know. Water is H2O. And we are going to get into this a whole lot later, but what this is basically saying, I think most of you know, is it's two atoms of this guy we call hydrogen, which is an explosive gas, very reactive, combined with one atom, a heavier atom, which we call oxygen, that we breathe. And so these things come together. Heat is involved in that reaction, and this guy is a molecular unit. That means that if we go and take a microscope and look at this, a sample of water, we'll see, if we could see molecules, right, because they're really small, but if we could see them, we would actually see little units floating around with two hydrogens and one oxygen. That's a molecular unit, right? And the properties of water have nothing to do with the properties of the things that make up the water. It's a unique thing that sort of has its own properties, its own melting point, its own boiling point, totally different from that of which it's made, which is why we have such an incredible variety of everything out in the universe here. Another example of a molecule might be carbon dioxide, CO2. The dioxide means two. Di means two. That's a prefix we'll learn a little bit later on when we really get into naming these things. This is just some quick examples. So we put carbon and oxygen together, we get carbon dioxide. We might also get, instead of carbon dioxide, we might get carbon monoxide, which is one atom of carbon for every one atom of oxygen. So you see, these are the same elements joined together, but we have two different stable molecules here. We have two oxygens along with the carbon. We also have one oxygen along with the carbon. So we have a whole potpourri of things that can be created here. In fact, some elements, I'll give you a little preview of something we'll talk about later, some elements can sort of form their own little molecules. Have you ever heard of O2? Oxygen, in terms of oxygen, you may hear in TV or something like, well, turn on the O2, or somebody's in the hospital, they'll turn on the O2 to the patient. That is oxygen gas. That's because the element oxygen, the thing that we're calling oxygen here, see, I just put O here on the board, but it turns out in real life, oxygen, along with a few other elements like nitrogen is another one, they don't really exist just one atom by itself. They really love to bond with themselves. I don't know why, they just love each other. In fact, we do know why. We'll talk about why later on in the course. But some of these atoms, if left alone, will just sort of pair up and bond, and that's totally stable. So when you get a bottle of oxygen, at the hospital, it's not pure single atoms of oxygen floating around in there. They're all bonded together in these little molecules of O2 gas. Same thing with nitrogen. You're always going to find nitrogen as N2, right? You're always going to find hydrogen as H2. Okay, not all gases do that, but some of them do. And we'll give you a whole list of which ones do that a little bit later in the course. But my point is we're talking about the concept of the molecule. So a molecule could be these guys right here, hydrogen, two of these guys bonding with oxygen. We could have carbon bonding with oxygen like this, two oxygen atoms. We could have one and one, or we can have the same atom bonded to itself. These are all molecules. So a molecule is just basically telling you that the atom can join and form these sort of larger units. So that's what we're going to talk about. We'll spend a good chunk of the whole course talking about molecules and come back to this later. Now, we're going to talk about the concept of a chemical reaction. A chemical reaction. What is a chemical reaction? I think most people have a really good idea of what a chemical reaction is, but just to make sure, what we're going to say here is that it occurs when matter undergoes a change in composition and or a structure of its molecules. All right, so that's what a chemical reaction is. Basically, you take two things, could be two elements you're putting together, could be two molecules of more complicated bindings of elements that you put together, and a rearrangement basically happens. When you take the vinegar which has a chemical, formula that we can write down on the board later. And you take it with the baking soda, which is another chemical formula that we can write down and talk about later. The details aren't important right now. We can take and put them together spontaneously because of the way the chemistry is involved. These guys really like to dance. So when we put them together, the electrons begin to be shared, the elements begin to be joined in different ways, and new products are formed, which are different combinations of those elements that have come together. And that's basically what a chemical reaction is. The oxygen in the air combines on the atomic level with some of the iron that's sitting in your front yard, and it produces iron oxide. That's rust. The properties of iron oxide are really not like iron. Iron is a nice shiny metal. Iron oxide is brown, rusty, brittle looking, powdery looking substance. And of course the oxygen in the air is a gas, so iron oxide doesn't look anything like that. Properties are totally different. But basically a chemical reaction is when matter undergoes a change of its structure of its molecules. And we'll talk about why later, but basically what happens is electrons begin to jump around, elements become reattached to maybe the other guy that you're mixing it with, and out spits new products. Okay? I'll say one more thing here. I've already hinted to it, but you may have something on your test. You may have something in your book. I just want to make sure there's no confusion. When we talk about the concept of an element, really, for the way I'm teaching it here, it's the same as an atom. All the periodic table of the elements, that's what we call it, the periodic table of the elements. They're all just different atoms with different number of protons and neutrons and electrons. We'll talk about all that stuff later. So, I could have kind of joined this with the definition of the atom, but, some examples of some elements would be, oxygen, like we talked before, nitrogen, sodium, which is Na, argon gas. What about neon, like a neon sign? Those are all different elements, which are all just different atoms. So basically, element and atom, for the purposes of a chemistry class, they're basically synonyms. So if you're reading a sentence and you see somebody talk about atoms, and you read another sentence and they're talking about element on the periodic table, you can basically just equate those two in your head. That's going to get you pretty far. All right. One more thing I'll talk about here before we move on to a different topic, and that is compound. It can confuse people at first. What's the difference between a compound and a molecule? Because most of the time, I'll tell you right now, most of the time, mentally, you can equate those two things. A compound and a molecule, more or less, you can think of them as the same thing, because they really are the same thing. One is a subclass of the other, really. Let's talk about what that is. A compound is a molecule, it's a type of molecule, in other words, where, let me put it like this. It's a molecule made up of two different elements. So honestly, it's really just a definition. And once you learn this, you probably never have to use this again. But let's talk about a couple of examples. CO2. Carbon dioxide. Two different elements make this guy up. Element carbon and the element oxygen, right? So because two different guys make this up, it is a compound, and of course it's a molecule. In other words, everything I list here is going to be molecules, because a molecule is the general term. A molecule is just sort of like any, when two things combine together, we say it's a molecule, right? We say it's a compound when the two things that come together are different elements. So let's give a couple more examples and I think you'll understand. What about water? We talk about the water molecule. So of course it is a molecule, but it's also a compound, because it's two different elements that form this guy. So you may ask yourself, well, if these guys are compounds and molecules, what could come together that would not be a compound? Well, the answer to that would be oxygen gas, let's say. I already told you that oxygen, when you get it in a tank, it's not just single oxygen atoms floating around. They're bonded together, always O2. That's why you hear it so much, maybe in the movies or whatever. So this guy is not a compound, but it is a molecule. Is a molecule. So in other words, like I said, all these things are going to be molecules because the molecules in general, when any two things comes together, these guys are not different. They're the same exact element, so we don't say it's a compound. Another example would be hydrogen gas or nitrogen gas. Anything that comes together that's the same element, it's not going to be a compound, but it is going to be a molecule. So because of that, there aren't too many things that we talk about that are going to bond together with itself. You know, these gases are some examples. There are probably some other examples out there. Most of the time, you can use compound and molecule totally interchangeably because most of the time, the elements that make up your molecule are going to be different elements, 99.9% of the time. But this is just a definition thing. So on your test, if you're asked, you know, what's the difference between a compound and a molecule? You'll know the answer. You'll know what the definition really is. All right. Let's go ahead and wrap this section up by talking about mixtures. What is a mixture? I think most people have a pretty good idea of what a mixture is. Mixture. It is when two, I'll call them substances, are, you guessed it, mixed together. And I'm going to go out of my way to say that there's no chemical reaction here. You know, the reason I bring this up isn't because it's terribly relevant to the rest of the course. Mixtures really aren't that terribly relevant, at least, you know, for now. But the reason I'm bringing it up is because almost all chemistry books have this in the beginning. We talk about mixtures, and that's just so that you understand that not everything that you mix together is going to react in a chemical sense. Let's say you have a bucket of water, you know, and then you take some sand and pour it into that water, or maybe some rocks, or maybe some flour or something like that, and you pour it in that water and you mix it up and it's a real nice mixture, but there's no reaction there. In fact, if you let that sand just sort of sit off in a corner by itself, that sand is going to settle right back down to the bottom and the water is going to be right on top. There's no chemical reaction, there's no elements that's, you know, doing any kind of rearrangement on any kind of molecular or atomic level. Everything is just sort of there and it's in the same space, but it's not actually chemically combining. That's what we call a mixture. All right. So to give you a few more definitions, we say that we have a homogeneous mixture. Okay. Homogeneous mixture. And that's a mixture that has the same composition everywhere. Okay, what would be a good example of a homogeneous mixture? That would be, an example would be salt dissolved in water, H2O. We're in chemistry class, so I'm going to start writing water as H2O. Salt dissolved in water. So the salt is not really chemically combining with the water. In other words, we're not forming a new compound with hydrogen and sodium, or, you know, we're not actually rearranging the atoms there to produce something new. But what does happen is the salt atoms sort of, they kind of fit between all of the water molecules. So that salt that you pour in there, it kind of disappears. Well, it doesn't really disappear. It's just that the salt crystals break down so small that the little atoms of sodium chloride, the salt, kind of fit between the water molecules. So we say it's dissolved. Now, if you take a sip of that water from the top, it'll taste pretty salty. Right? Now, if you take a straw and put it to the bottom, assuming you've mixed it well, then you take a sip from the bottom, it's going to taste pretty salty. More or less, it's going to be the same saltiness as the top of the water, from the bottom of the water. So the mixture, so to speak, has totally and evenly distributed everything everywhere. So it's the same consistency at every single point. Totally unlike the sand that we talked about a minute ago. That's not mixed well at all. It's totally separated. But the salt example, everything's mixed together well. So we call it a homogeneous mixture. The prefix homo means the same. So when you think of it that way. Homo means the same, so it's the same composition everywhere. So since we're talking about different kinds of mixtures, we have a homogeneous mixture. Then you would also have a heterogeneous mixture. right? And so from this example, you probably should be able to figure out hetero means different. So what this means is that the mixture varies in composition from place to place. Okay, and the example that we just talked about is sand in water. Yeah, you can mix it up really well and it'll look pretty good, but after 5 minutes that sand is going to settle to the bottom, so that's heterogeneous. Rocks in dirt. You don't have to have a liquid to have a mixture. I mean, you can have potting soil, dirt, and you can mix some rocks in there. But unless you mix it, you know, incredibly well, the odds of the composition of that mixture being exactly the same everywhere are pretty low. Especially if you just pour some rocks in there and give it a little bit of a stir. You're going to have some clumps of rocks over here, some clumps of rocks over here. It's not going to be totally evenly distributed. So we call it a heterogeneous mixture. Well, that about does it. This is a good introduction to chemistry. I hope I've given you a little bit of motivation. Chemistry is something that you see every day. It's all around you. Every time you breathe in a breath of oxygen, that oxygen goes into your cells. There are chemical reactions taking place that basically turn that oxygen, and they basically burn the fuel that we eat and drink every day, make energy, which allow us to move and walk around. You know, we may build a campfire. That's a chemical reaction there that's liberating energy from that wood, from the chemical reaction that goes on between the wood and the oxygen. So what we're going to do in the remainder of the course, we're going to cover some foundational material first, and then we're going to talk a whole lot about the periodic table and I won't say all the elements, but we're going to go through the most important elements that you'll use in your chemistry class regularly. Talk about the structure, how the periodic table is put together. We'll talk then about how these elements come together to make these molecules. I mean, we've kind of given you some examples, but we want to be able to predict. We want to be able to know what's going to form if we mix these two elements together, right? And will they form anything at all? Some things won't form anything if you mix them together. And how is that the case? So we're going to talk about that. After we do that, then we'll expand our scope a little bit more, and we'll talk about taking molecule A, which let's say it's water, and then molecule B could be some other molecule that we have, you know, sodium chloride, you know, potassium hydroxide, whatever, and we mix them together. Will they react? Will they form a new product over there? And if so, how much product will form? If we have X number of grams of things that we're mixing together, we call those the reactants. The thing that we mix together, we call them the reactants. How much product are we going to produce in terms of grams? So that's where we're going. We're going to go talk about elements, compounds. We're going to talk about mixing these compounds together to make a chemical reaction, balancing the chemical reaction, and computing what comes out on the other side. I'm Jason. I hope I've given you a good introductory lesson to chemistry. Stick with me. We're going to go through every single topic step by step with lots of examples to make sure that your chemistry class is enjoyable and that you know how to do well in your lectures, on your quizzes, and on your exams.